So good morning. You must have gotten 3 handouts, one for Friday, one for today, one for Wednesday, and the exam solutions and the grade distribution, right? You didn't get what? So if you didn't get it, it probably is here, right? Or if it's still going around. So the average grade for the exam went down. I mean, it's actually, I think, closer to 0 than before, right? So I can't figure out if it's because people decided not to attempt stuff and then go for the 0. It's not really 0, right? It's basically 3 out of 6. But 2 of you got it all right, but some of you didn't get it all right. So not all right. I mean, this I think they got 1 right. So we can go through the solution. So was that style of exam more harder than what you are used to?
Yes.
Which part? The negative part or the true or false part? I'm sorry?
Multiple choice part.
Oh, multiple question. Okay. So I think naturally, like the final exam and the one before that would be more of a, not true false, but you giving a little bit, I mean, little paragraph of text, right? Because that's kind of logically how the course goes. So the one on file system would logically be like a true or false, but let me think about it, right? So, but the overall grades, if you look at the class, it kind of, I mean, you know, I think it's a pretty nice curve. Obviously, there are a few at the bottom, and so if you're sort of, there's a little drop at the bottom, and you know, there's a few students there. So if you're one of those, talk to me, and we can figure out what it is. But the top half, it's kind of hard to tell. I mean, it's so close together. So essentially, if I were to give a grade right now, it's kind of hard to kind of figure out where to stop with the A, right? It's kind of goes like that. So I'm not too worried about the overall class performance looking at this graph, but the exam graph sounds cute, right? So the first question, I think most of you got it right, right? Because you can actually create a larger page from a smaller page. So actually, some of these answers, I think I gave it away on the lecture or two before the exam, right? I don't know how many of you noticed it, right? So actually, I think for the later half, I actually said what the answer was as part of the lecture. But for the first part, first question, right? So you can make larger pages in the operating system. So essentially, you can protect all of them together. You have to remember to protect all of them together, or do what have you, right? So you can actually create a larger page than what the physical hardware provides, but you can't make it smaller because then you won't get the page fault, right? So you essentially need, so this goes back to the point I was trying to stress, which is OS can only do stuff if it gets control from the hardware. So as long as the hardware can somehow tell the OS and still get good performance, you could do that. So if you make the pages smaller, then you would not get a page fault unless you make the page invalid all the time and you keep getting page faults all the time, right? So some of you answered that you can only do, you know, when they equal the same size, but actually you can make it larger, right? In fact, this is what you do for the file system too, and we'll actually go through them on Wednesday. So the hard disk provides sectors which are 512 bytes typically, but the operating system can create any larger size. You can't make it smaller, but can make it larger, right? For the second part, so for the second question, some of you got the answer that B is right? B is actually a little trick question because B basically says that the hardware is not restarting the instruction properly, right? There cannot be a race condition within the hardware. So the hardware says that until all the memory pages are there, it can continue the execution. When you do re-execute of the instruction, you can't have the case I'm talking about, right? That shows that the hardware is not working properly, because the hardware works properly. However many times you restart it, it should still not proceed when conditions are changed, right? So you may not be able to make progress, but the hardware cannot let you do partial computations. So you have to trust that the hardware performs fine, so that cannot be true. And the third part is a little trick question, because essentially I'm asking you to compare it with the optimal solution, right? So you should not be able to do better than the optimal solution. If you do, then that's not optimal, right? So as a random policy, we can't really say too much about precisely how it's going to behave, because it can behave optimally, it can behave suboptimally, but it can't behave better than optimal, right? So that's a part with the C. So essentially, A is the only thing which is left, and A basically says that it may not. So I'm not exactly saying it won't, right? Because it's a random policy. So depending on what that random turns out to, you may exhibit the anomaly, you may not exhibit anomaly. But you know for a fact the other two cannot be true, right? You cannot be better than optimal for any algorithm, and you have to trust the hardware, right? Yeah, so the third part, most of you got it right, or didn't answer it, right? So essentially, if you to increase your working set, if you're making function calls and stuff, so as long as your code is like randomly going around all over the place, either using gotos or function calls, or the first time you're entering a while loop or something. So as long as you are going all over the place, you tend to increase the working set, right? When you're going in a while loop for an hour, you won't increase the working set, because your working set is constrained to those instructions. But any of the other ones can increase the working set. The next question is actually from your exercise from your book. I think most of you either got it or didn't write at all. And the fifth part, right? So many of you got it, and some of you didn't get it right. So the notion of logical address space, how should it be compared to the physical address space, right? All the examples we talked about would assume that logical address space is larger than the physical address space, right? But there's no reason why they should be, that relationship should hold. It can actually be equal, or it can actually be smaller, right? And if it's smaller, then you have to figure out what to do with it, because essentially your program can only address a certain chunk of the main memory. The main memory is a lot larger, right? So you have to have some other mechanism so that you can use the rest of the main memory, right? Regardless, you're still allowed to have a larger space. And the sixth question, many of you got it wrong because you quoted something from the textbook which says that every time you do a context switch, you have to flush the TLB, right? It goes, again, going back to the notion of when the OS gets control. If you're running a user level thread library, OS does not know when you're doing context switch, right? So OS cannot flush the TLB when you're doing context switch within the user level process. With the kernel level process, it only has to flush the TLB if you're context switching to a different process, not to the same process, right? But at the least, for the user level threads, the OS cannot get control. So OS cannot really flush TLB entries, right? So, and the last one, most of you got it right. Either answer it as decrease the CPU utilization or not, because essentially the bottleneck is the paging disk. So making a faster processor would make you do the work, finish the work faster, and then wait for the disk more. So either you can consider that as the nothing changes, or the CPU utilization actually goes down because you're now finishing the job faster. Right? So, like before, if you have any questions about grading or anything, talk to me either after the class today or actually on Friday. And if you're finding the class too hard or something, drop by and chat with me and see what you can do. Right? Yes.
Just one quick question. Where can we find out those grades?
send me an email. I have it in an Excel spreadsheet, so I'll give you the what your grades are. Right? So, yeah, at some point I would want you to drop by and check to make sure that my records are the same as what you have, right? But for now, you have to send me an email. So before I continue back with the file system implementation stuff, do you have any questions from the what we've done so far? So the multiple choice questions, don't the other classes have multiple choice type of questions? They do, right? Multiple choice questions?
Oh, yeah. But like usually all the answers can't be right.
Oh. Okay. I think many of you answered something wrong. So if you had answered part of the questions right, then talk to me and I'll see how far you went. But if you answer something wrong, I cannot possibly give you partial credit, right? So if you say something which is blatantly wrong, then your grade will stand. But if it's all of them are true kind of things and you answer just one of them as true, right? So if your answer is correct, but not all the way correct, come and talk to me. But if your answer is wrong, even if it's partially wrong, right? So if you answer 3 of them are right and one of them is wrong, then I can't do anything about it. Yeah, these sort of exams are typically harder because you actually have to kind of know precisely. So that's why I was kind of giving hints on the last lecture. So if you actually looked at the last lecture before the exam, right? So we actually, I didn't say it like the exam, but I was basically saying give you the answers to, I think, a few of them at the bottom, right? So getting back to the file system implementation. So so far we're trying to look at what are the notions of files and directories and how the users use them and stuff. And so right now we're looking at how you may implement some of these stuff, right? So on Wednesday we'll go over the storage like this and what have you, and trying to map what we want to do with some of these devices, right? And unfortunately, I won't be here on Wednesday either, so it's again going to be a video lecture. The TA will be here. And so if you followed along, one of the changes I'm making to the course towards the last, I'm getting rid of the stuff on distributed systems. I think that was the last 2 lectures towards the end of the course, right? I'm going to get rid of the distributed systems constructs and changing that to designing operating system in class. So we're not going to write code for it, but essentially talk about if you have a laptop, set a bunch of parameters and say what kind of parameters we would choose. For example, if your laptop, would you turn on logging or not, kind of stuff, right? So we'll go through 2 of those. Hopefully that'll make many of the stuff we talked about in abstract sense more concrete. So we'll go through a PDA, laptop, desktop, and a server. So I'm going to replace the section on distributed systems with that, because distributed systems, you are going to probably spend way more time in your senior level classes, and it's a lot more interesting to make this stuff clear, right? So when we finish stuff here, we're looking at how to organize files in an indexed data structure. We didn't actually go into it. We just started with it. So we are trying to figure out how to allocate more data blocks to a file, right? And the goal here is you want the file to be able to grow as big as you want. So you want the ability to grow the file size, and while it's still at the same time getting good performance, right? And the performance penalty here is every time you have to go to storage medium, the program slows down. So you want to keep these things as contiguous as possible. So you don't want to go to the disk. So you want to either be able to go to the storage media the least amount of times, and while you are at it, you want to read as much as possible, right? And we'll see on Wednesday's class why that's important. The idea here is you pay a lot of cost to get the head to where in the disk that you want to read. So while you paid all the cost, you want to use that to read as much data as possible. So you don't want the data to be spread all over the disk. So the next allocation so we looked at contiguous allocation and extent-based allocation in the previous lecture. So now we continue with the index allocation. So essentially, index allocation, you create one data block which has pointers to all the other data blocks. So essentially, if you want to look at the data, which is all the ones where the arrow points to, right? So if you want to look at the first byte of the file, it'll be on the first pointer, and after the sort of the data block size, it goes to the next one, and so on. So this way, in this case, you can address 5 times the data block size using this mechanism, right? If you assume that you have 5 pointers in one block, so essentially your file can be at most 5 blocks, right? And of course, you have variations of this which will make this possible. So essentially, so in this notion, if you have a file called Jeep, and the index block's at block 19, right? And 19 has a bunch of pointers. So for example, if it was like this, so essentially the first block of data is at block 9, second is at 16, third is at 1, 10, 25, and then -1, -1, -1, something invalid. So essentially, the file is 5 data blocks, and they're spread all over the disk, right? So like I said, this may or may not be good for the underlying hard disk, but essentially this lets you create a file, by basically having these pointers, right? And this is not related to what we're doing in the operating system. So are you aware that you can actually create files with holes in them, right? So essentially, you can create a file. So in this case, right, I can create a file with 19, 16, 1, 10, 25, -1. So this is possible, right? Have you used them in your programs to generate a file where something is in the middle is invalid and something in the end is? Right? The way you create that is to do a seek. So if you do a seek and then write, so if you open a file, right, and then you seek to say 1024, and then right, if you do this, essentially you seeked into somewhere in the middle of the file, you wrote something, and then you closed it. So if this is all you did, right, from 0 to 1023 is undefined, right? You may get a 0 when you read it, depending on what the operating system wants to give you, but there should not be anything allocated for it. So OS may actually have holes for those, right? So even though a file may be, so in this case, if you wrote, say, like 10 bytes, right? So your allocated space should only be 10 bytes, or whatever your block size is, even though your file would say it's of size 1010, right? So, and that's one of the reasons why you have all these negative ones. So you can actually have a file which is larger than how much data you have. So this is the start of how you would build more complicated. So with this, you can only have a file which is as big as the block to create these pointers. And the cool thing is, you can do random access, because essentially when you read the index block, you can index into that to go wherever. So if you want to go read the data which is on the 5th block, you essentially read the 5th entry and go read that. So you get good random access, but it tends to distribute the data all over the disk. So the way you build more complicated data structures is to have multi-level trees, right? So essentially, you create index of index and index. So you have, for the file, you have a, inner level index, outer level index. You can create as many indexes as you want. So if you want to look at a file, if you want to operate a data file, you first figure out where the outermost index is, read that index to figure out where the file should be, and then read the next index table and so on. Right? So you can possibly have the first 1 gigabyte should be on. So you can split the 3 gigabyte. If you have 4 gigabyte file, right? So you could split them into the first gigabyte should go into the first index table, second gigabyte should go to the second index table, and so on. And over here, you have another index table which points to the data block, right? So if you were to seek into, you still have the random access, good random access behavior. So because if you want to read something which is more than 3 gigabyte, you directly read this entry, and from there go to the corresponding index table and so on, right? So this way you can grow the file. So depending on, so all this are constrained by how big the block is, right? So the block decides how many pointers you can have in this index table, which decides how many layers you should have. The more layers you have, you can possibly address a larger address space, but they also tend to be slow because so if you open a file and read 1 byte, right? Now you have to first read that outer block and then read all the index blocks to come to the actual data block. So it could be potentially slow for a small file, but it may not matter all that much for a large file. So if you're reading a 1 gigabyte file, then the cost of this gets amortized, right? So this brings up the same issue we had before, right? All the policies that we learned have to map into real machines. So depending on what you do, some of these policies may or may not be applicable, right? And that's one of the reasons why I want to change it to talk about how you would do this for different machines and stuff. But essentially, the policy depends on what you're trying to do. So if most of the files in your machine tend to be small, then this approach would be really, really bad, right? So if all the files in your system are 1 byte, then if you want to read all the files in your system, using this approach can be the worst, because every time for every block, you have to read 3 other blocks, and that can have really bad performance. If all the files in your system are fairly large, then this doesn't matter. I mean, the cost really doesn't matter because you tend to actually use a lot more of these pointers, so you don't have much cost, right? So people do a lot of studies trying to figure out what are the typical size files in a machine, and that depends on what kind of machine you have. So if you have a Windows machine, or if you have a Mac machine or Linux machine, you have to figure out what are the types of files you have and how are these accessed, right? There's a lot of research done, people published papers, and this is something that you can actually go through your system to figure out what kind of files you have, right? I encourage you to, whatever machine you have, whatever operating system you have, try to look through them to see what kind of files there are and what are the file sizes and stuff. So that'll give you a sense of what kind of allocation mechanism you should use for your particular system, right? And the assumption is most of the desktops have lots of small files which are open and then closed frequently, right? People typically don't have large files. Of course, it's not true once you have video objects and stuff, but as long as you don't have those, if you have a lot of text files, they tend to be fairly small. So if the OS designers think that you're going to have small files, then they won't choose this mechanism, they'll choose a variation of this mechanism, right? The variation of the mechanism is what was being used in Linux, or Unix in general, right? So they made the observation that a lot of files are small, but there are few files which are large that you tend to use a lot. So you want to have the best of both worlds. So you want to be able to access the small files fast and still be able to grow to a large size, right? So the way they solve the problem is to have multiple levels for multiple size files, right? So essentially, this is the inode structure, which is the main file control block structure. So you tend to have a few direct blocks directly in them. So for every file, you have to read this inode structure to figure out something about the file, whether you can open the file and whether you have the privileges or not. So you're going to have to pay the cost to read the structure anyway, right? So once you pay the cost, you leave a certain number of direct block pointers right in the file, right? So if your file is very small, essentially all your file would be directly mapped from the direct blocks, and your performance should be good, right? So for the files which are larger, you have a single indirect pointer, one single indirect pointer. So essentially that gives you a way to access larger files going through one index file. And you also have a double indirect and a triple indirect, right? Triple indirect would mean that you go to an index which indexes to another index, which indexes to an index table, which indexes to the data block, right? So if you have a really large file, right, after certain offsets, you'll go through the triple indirect block. So small files would go to direct block. Medium-sized files would have one level of indirection. Slightly larger would have 2 levels, and a really large file would have 3 levels of indirection. Right? So this is a way to get the best of both performance. So it's indexed, but sort of like the single and multiple indirection. Right? So again, these things happen after you figure out what typical files you expect. So if you're operating on scientific databases or something where all the files are large, then you may not really want to do all the stuff, because you don't expect any files to be small. You expect all files to say be 4 gigabytes or something. So you may directly go to a triple direct data structure. But a general purpose file system like Unix file system has to assume that you have small files and large files. Does that make sense? So far we have looked at how you would assign the data blocks to a file, right? So we first talked about how do you organize directories. So you have directories where you have the file control block entries, either linearly or hashed, right? So once you have those entries, we talked about how you would allocate the data blocks to the file, either through indexed or through contiguous allocation, right? So at this point, you should be able to have a notion of a directory and files in the directory, right? So you first read the directory, either search through them, whichever way you have to, and then once you get the first pointer, you can either have something which is hybrid like this, or whichever way to figure out where the data blocks are, and you read them or write them to access the files, right? So the next operation is trying to figure out where the free blocks are. Right. So when a file request comes in, the system has to give you has to tell you which blocks are free, so it can be allocated to a file, right? And you want to make sure that this operation is safe, because there are a couple of scenarios, right? One scenario is you have a block, right? And let's say you have a file, right? So the right case, maybe the file should point to here, right? The wrong cases, maybe another file points to here because it did not know that this block was occupied. So the allocation policies did not work correctly. So this was allocated to another file too, right? Because the system thought it's a free block, it gave it to another one. So essentially you have 2 files pointing to the same data block, and that's not good, right? That essentially means that both of them can read and write these contents because the system did not know that this was occupied. So this should not have happened. What should have happened is you should have had this pointer pointed to a new data block, right? So it's essential for you to maintain this free list consistently somewhere so that you know not to give the block to somebody else, right? You had the same problem when you dealt with shared memory too, but at least in that case, once you reboot the machine, things are back to normal, right? But in this case, if you write it to the disk, it's stuck there. So at this point, if this is all you see on the hard disk, if you see blocks pointing to the same thing, right? You have no way of knowing where this block belongs to. So both these files are suspect now. I mean, so it has to be given to you and for you to deal with, right? And you may have seen some of these things happening in your, depending on the operating system you use, right? They may have notions of check disk, FSCK, or something, right? So if you crash the machine before some of these things are fully written, right? in Windows, if you pull the plug while the machine is still running, right? When it comes back up, it'll say you need to do check disk, and then it goes through something, and then you see these little blocks, right? It'll, I think, cause it check disk. So not just for this case, but different reasons. But essentially, it tells you that there's something not right here, because it doesn't know what to deal with that, right? So it may give you those files as a separate block and say deal with it. Either how check disk does it. Unix will put it in last plus found directory. Different operating systems deal with them differently. So it's important to get this stuff right? It's also important to write it onto the hard disk, because this is the only data structure where the disk knows what the free things are, right? So there are two ways to figure out what are the free disk blocks on the size. One is to go through all the files, right? When you boot up the system, go through all the files, and from each file, go through, read all the indexes to see what are the data blocks associated with them, right? And try to build the index of all the data blocks which are being used to generate the free block size on the fly. Does that make sense? Right? So we need to keep track of what are the blocks which are free for a particular file system, right? So the one way to do that is to do it dynamically. So every time you boot the system, right, you read all the files in the file system and follow through all the data blocks to see all the data blocks that are being used, right? And keep track of them so you can figure out what are the blocks which are not being used, and those are the free blocks. If you do them like that, every time you boot the machine, your system will go crazy trying to read all the files, right? And it's not a good solution, especially with these larger disks. So if you have a 1 terabyte disk or something, right, you're going to sit there forever while it's trying to read and generate all this stuff. So the approach that you typically use is to write this back into the hard disk, right? So you don't have to do it on the fly. You do it only once, and it's updated on the hard disk, which makes it even more important for this to be on the disk, because if this gets messed up, then a whole bunch of other things go wrong, right? So one way to do that is to keep this information as a large big bit vector, right? Which essentially you create a long bit vector where each bit corresponds to a certain block. So if you see that the block 0 on the disk is free, then you reset the corresponding bit on the bit vector, right? So the bit vector has to be as large as the number of blocks in your disk, right? So if you want to figure out if a particular disk is free, so or if you want to find a free block, right? Essentially start from 0 and keep going till you find a 1, right? So you can do a bit operation on all the bytes one after the other till you find a bit which is not 0, right? And then you can figure out which bit within that field is set, and you know that is free, right? Yes.
Why not just keep like a list of blocks that are free at that level?
A couple more slides. That's another option, right? So the good thing about this approach is you tend to kind of search and find out. You can find out contiguous spaces easily too. Right? If you want a contiguous set of stuff, if you have a bit vector, then essentially you're looking for a certain number of ones together. So if you want 8 bits together, then you're searching for 8 bits together, right? And as you'll see, index is a lot harder to maintain that. So going with the bit vector approach, the bit vector takes space which is wasted space, which may or may not be a bad thing from your viewpoint, right? So if you have a 4 kilobyte blocks, right, and if you have a 256 gig hard drive, one of those things, right? So essentially you waste 8 megabytes for the bit vector, right? And 8 megabytes is used for this bit vector. So more importantly, you may want to keep this in main memory for operations, because you tend to go through them fairly often. But it takes that much space, right? So yeah, the good thing about them is you can find contiguous spaces easily. So if you want a bit pattern of 8 ones together, so you search for that 8 ones together. If you want just one block, you get that one block. So you could do something about clustering itself. So if you have one file in certain block, if you want another block which is close to it, you can essentially go to that particular bit and then try to look around that bit field, right? So, because since you have a map of the whole disk, right, you can figure out where you want this context, right? So you have some notion of where you want them, and you can enforce them, right? And so again, you know, staying with the bit field, right? So so it's very important for you to keep this data structure consistent on the disk, right? So what you don't want is, you know, in the bit vector, you find a bit was 1, right? And you decide to allocate it. You allocate it to 0, give it to a file, and the file starts to write something into it. The machine crashes, and this was never returned back into the disk. So on the disk, it still is 1, right? Meaning it's still free, right? So the next time the machine boots up, you'll think it's free, and then, you know, bad things happen, right? Can you figure out if this happened while you're booting up? Right? This is what is in disk, and when you boot it up, sorry, before you boot it up, it was like here, right? Which meant that file 1 points to block 3. That's it, right? So this is what happened in the memory, right? The file was pointing through this block, and because it is allocated here, let's say this is 1, 2, 3, right? It is allocated here, right? And the machine crashes, right? So we lost this. So now we come back, and you only have what is on disk, right? So you essentially have something which says that this block is free, right? How would you notice that this is happening? When the system boots up, how would you figure out this happened? Yes.
If there's a file allocation table that tells you what files, like what, you know, the directory structure or the structure that's linked to that file, and you compare that to the free space, you know, bit vector, and they're different than something thrown.
So essentially, you go through the file allocation. You go through all files, right? File allocation table essentially gives you all the files. So essentially, go through all files and try to see what blocks they're using, and if one of the blocks that they think are using is not, if there's a consistency here, you notice that, right? Which is sort of like what you're saying, right?
Right.
So it's a very slow operation. So you have to go through all files in the system, see all the files all the blocks that the files think that they're allocated to it, and if a file thinks that it has a block and it's not, it's marked as free, then we have a problem. And some of them can be automatically repaired, some of them cannot be, right? This particular case can be repaired because then you basically make it 0 because you trust that this is correct, and then you move on, right? So the way you solve that is to try to first, define an order. So you set the block to be, meaning it's allocated onto the disk, allocate the block, and then set it to 1 on memory, right? So what happens if it's the other way? So what happens if the machine sets basically sets this to be allocated on the hard disk, right? And before it gives it actually to the particular file, it crashes. So the file doesn't point to this yet, right? This block, it says it's allocated, writes it into the hard disk, and before it can be given to this file, right, essentially writing into its data structures, system crashes. What would happen to this block?
The data is kind of worthless because the system may know that it's supposed to be allocated, but if there's no references in the file allocation table, it doesn't know where the file continues, where it starts, or what its purpose is.
Yeah, so you have a dangling block and it's not being used by anybody, it's out there, right? So how many of you have done FSCK or check disk on systems? You probably would have done it a lot more time, but how many of you actually notice what it's saying when you're doing the stuff, right? So it'll say some information about checking the bit vector, checking the free blocks, and checking for orphan nodes and stuff like that, right? So these are basically orphan nodes. These are not bad from the system perspective. I mean, these are blocks that are not being used, but at least they're not causing any damage, right? A file block pointing to a unallocated block, that's bad because another file can point into the same data and then change this contents, right? How many of you noticed that? Like you have a file and suddenly in the middle of the file you notice something, some garbage, something that you don't know. It may be a C program or something show up in a different file. You haven't noticed it? It happens far too often than that, right? It happens far too often where things go wrong and stuff, where you point to the wrong stuff, right? It also happens because of bugs in operating system, right? Mac OS-X for the first couple of iterations used to have that problem. They both point to the same structure because something got messed up, right? And it's really annoying to fix because both the files are essentially useless now because you don't know which block is what. So you are free to go through them manually, figure out which block is what, and put them back together, right? But I can assure you it's not really fun to do that. You basically have blocks from different files kind of interspersed. You can, if it's a text file, you can do something about it. Right? So the next, the linked list arrangement is what you were kind of pointing out, right? So you can keep a list of the free blocks and then essentially trace them to figure out what blocks are free. And following pointers may mean that you have to. So getting a contiguous set of stuff may mean that you have to start from the start. So getting a free block may be easy because keep track of where the last pointer was and go to the next one. Getting a set of some blocks with a certain characteristics would mean different things, right? So another question. So judging by the way that, and I'll wrap up after that. Judging by the way the blocks are freed, right? Can you undo files in certain kind of way, right? So if you know that the files are being allocated on using a bit vector, or file is being allocated and freed using a linked list pointer, right? And you know that in the bit vector field, you always start, if you want a free block, you always start from the initial 0 and then keep searching till you find the block that you want, or in a linked list structure where you start off at some point, right? So linked list structure, you have to have a mechanism to add the new free blocks into the system and start using them, right? So would one of them have significance on what happens when you delete a file and you want to undo it, right? So when you delete a file, all the blocks which are held by the file are released to the system, right? So they essentially go back to the free pool, right? So if you want to undo it, you have to first resurrect the file control block. I know the control entry, right? So assume that you get that, right? Now you have to chase the system. You have to race to get all the data blocks that were allocated back to the file, right? Right. So that means before somebody else uses those blocks, it should be given to you. You should be able to get them back to you, right? Do one of these schemes help you or hinder you in doing that? Which one would you choose if you want that ability? Or which one would you choose if you don't want that ability? You don't want the ability if you're if the FBI is going to subpoena you and you want the data to be erased, right? So you want the stuff to be allocated to something else as soon as possible, right? We can continue with it on next class, right? There's no right or wrong answer, but I think the linked list pointer would, you can make it so that you keep it for the longest. If you keep adding the files towards the end, then essentially you have to allocate everything else before, coming to the entry it's basically first in, first out, so you have a chance to go back and get it, right?